10 million aluminum cans are discarded across the globe every single hour. This volume of metal waste is so immense that it could theoretically submerge an entire metropolitan area the size of Los Angeles under a dense layer of discarded containers. Why is the secondary processing of this material considered one of the most efficient industrial cycles in existence? The answer lies in the atomic structure of the metal itself. Aluminum possesses the unique physical property of being infinitely recyclable without any degradation of its primary mechanical characteristics or purity. The rebirth of these supposedly worthless objects initiates within the complex infrastructure of automated recycling facilities. One can notice how massive conveyor belts transport thousands of units into high-speed sorting chambers. Here, the material is shredded into small fragments by rotating steel blades and systematically purged of coatings or organic impurities. The process is only gaining momentum. These cleaned particles are then transferred into melting furnaces, where temperatures reach 700 degrees Celsius. Step by step, the liquid metal undergoes chemical refining until it attains the precise specifications required for high-grade industrial applications. 70 million tons of aluminum are manufactured globally on an annual basis. This staggering quantity highlights the absolute necessity of the metal in the construction of window frames, automotive chassis, and even the pressurized fuselages of modern aircraft. But such industrial power comes at a price in the form of carbon dioxide emissions and the rapid accumulation of scrap. It only looks obvious to keep mining new resources, but in reality, the environmental and economic pressure makes the circular economy unavoidable. At present, approximately 35% of all aluminum utilized by global industries is derived from recycled sources. The efficiency of this cycle is dictated by a stock energy contrast. Producing aluminum from recycled scrap requires only 5% of the total energy needed to extract the same amount of metal from raw bauxite ore. This 95% energy saving translates directly into a massive reduction in operational costs and atmospheric pollutants. It is estimated that 75% of all aluminum ever produced throughout human history remains in active circulation today. The camera glides along the discharge channels where the molten stream is cast into new ingots. This material is ready to move to the next processing phase without haste. Tens of millions of tons of aluminum are collected every single year from an interconnected network of diverse sources across the United States. Why does the recycling process begin with such an emphasis on massive collection volumes? One might assume that extraction from mines is more efficient, but the sheer economic value of aluminum scrap dictates the entire flow of the domestic industry. This metal possesses a built-in market worth that exceeds that of plastics or glass by several times, providing a constant financial incentive for both municipal sorting facilities and large-scale industrial networks to funnel material back into the production loop. The United States currently stands as the global leader in this sector. Long lines of heavy-duty trucks roll steadily into vast staging yards from collection hubs scattered across the entire nation. One can notice how each vehicle is first weighed on precision scales and recorded before the hiss of hydraulics signals the slow tilt of the container. The load is released onto heavy-duty conveyor systems that transport the metal into designated storage zones. But this is just the beginning. It seems simple to just pile the metal together, but in reality, this stage shapes the effectiveness of every subsequent mechanical process. Vast heaps of gleaming metal rise across the site like silver hills, comprised of a mixture of used beverage cans, residential food containers, and precise aluminum offcuts from manufacturing plants. Technicians on location carry out rapid initial inspections of these heaps to ensure the purity of the intake. They quickly identify and turn away any shipments tainted by dangerous substances or excessive non-metallic contaminants. The facility operates as a relentless gateway, receiving thousands of tons of material every single day to maintain a reliable domestic supply for heavy industry. The process is only gaining momentum as the metal moves toward the sorting lines. Continuous streams of aluminum scrap move along extended conveyor belts that rotate without interruption. Optical sensors, functioning as high-speed digital eyes, scan thousands of individual pieces every second by analyzing their specific reflective properties and coloration. It is visible how powerful magnets suspended above the line extract any ferrous metals, while precisely timed bursts of compressed air propel the aluminum away from paper, plastics, and other lightweight debris. Layer by layer, the automated separation system breaks down the chaotic blend into a uniform flow. Everything only gets more complicated as the purity requirements increase. At first glance, the sorting looks like a blur of motion, but in reality, it is a sequence of millisecond perfect mechanical actions. The equipment gradually refines the stream until the aluminum gathers into organized, shimmering piles of nearly pure metal. This material is now chemically consistent and strictly regulated, moving further along the conveyor toward the next phase of its industrial rebirth. The sorted metal is ready to leave the intake zone, transitioning into the melting stage, where it will eventually take on an entirely new form. 660 to 750 degrees is the exact thermal range maintained within the heart of the melting units. Why is such a narrow temperature window strictly enforced during the smelting of aluminum? The metal seems robust in its solid state, but it becomes volatile once it reaches a liquid form. If the heat rises even slightly above these parameters, critical alloying elements begin to vaporize, destroying the chemical integrity of the entire batch. Hundreds of kilograms of separated scrap, including food containers and industrial offcuts, are directed into a massive shredding unit. One can notice how conveyor belts continuously drop the material into pairs of counter-rotating steel rollers equipped with hardened teeth. Under extreme crushing force, the aluminum breaks apart instantly, while sharp metallic impacts ring out across the facility floor. The process is only gaining momentum. Automated systems run with remarkable accuracy as spinning blades and heavy crushing hammers work alongside the rollers to fracture even the thickest rigid components. Beneath the harsh glow of industrial lights, one can notice streams of silver fragments flowing non-stop and spilling onto the lower conveyor like a glittering cascade. A vibrating screening system then regulates the output size, ensuring every piece of shredded aluminum reaches a uniform dimension. It gets more complex further on. Shredded fragments are fed directly into large-scale industrial furnaces, which serve as the core of the recycling operation. The facility may rely on reverberatory furnaces, rotary kilns, or electric arc furnaces, depending on the scrap type. Each unit functions as a sealed, precisely engineered system designed to regulate temperature, airflow, and the rate of material mixing simultaneously. Transition to the next level. The aluminum is introduced through a top hatch or a tilting chute and kept in constant motion by mechanical agitators or controlled air injection. It only looks obvious to melt the metal, but in reality, some furnaces must incorporate heat recovery technology to maintain energy efficiency. Multi-stage filtration systems clean the exhaust gases, capturing aluminum oxide dust and neutralizing emissions while the material liquefies. Thermal sensors and chemical analyzers run without interruption to ensure every batch of molten metal meets strict technical standards. One can notice how the camera glides along the control panels, where pressure, heat, and chemical reactions converge in a single climax. A single mistake in these calculations can ruin an entire melt. But this is just the beginning. Even after the aluminum has completely melted, it still holds countless contaminants like oxides, furnace dust, and traces of oils invisible to the naked eye. To remove these elements, the facility performs a refining stage directly inside the furnace. Fluxing is the most common technique, where a specially formulated chemical flux is added to the melt. As it reacts, the flux binds with impurities to create a lightweight dross layer. Slag floats up like silvery foam to the surface of the liquid metal. This layer is then skimmed away either mechanically or by hand to leave behind a purified material. In more advanced setups, inert gases like argon or chlorine are injected at low pressure. Tiny bubbles pass through the molten aluminum, capturing excess oxygen and hydrogen and lifting them to the surface for removal. Everything only gets more complicated as the metal reaches its final purity level. The outcome is a continuous flow of clean, molten aluminum, ready for the next stage of transformation. The liquid metal is now prepared to take on its new form without any remaining traces of its previous life. This stage concludes the primary purification, opening the road to casting and formation. 100% of the molten aluminum must reach its target purity before it is routed into the casting area to acquire its first clearly defined physical shape. Why is the transition from a liquid state to a solid mass considered the most critical phase of production? The metal undergoes a fundamental shift from a formless mass into structured units that can be measured, handled, and transported across the facility. But this is just the beginning. It seems simple to pour liquid metal into a container, but in reality, the aluminum is directed into molds made from steel, graphite, or other specialized heat-resistant materials, tailored for the final product. The equipment gradually fills vertical molds for ingots, horizontal molds for thick slabs, or continuous casting systems that utilize water-cooled, forced solidification. One can notice how the pouring speed, mold temperature, and cooling intensity are all finely tuned by the control systems. If the metal flows at a rate exceeding the calculated limit, gas pockets or surface cracks can form immediately. If the mold temperature drops too low, solidification occurs unevenly, creating internal defects deep within the structure. Every variable must remain in perfect balance. The process is only gaining momentum. In many modern plants, casting is fully automated, yet in some semi-manual operations, experienced workers still regulate the flow themselves with split-second precision. It only looks obvious that the metal will take the shape of its container, but any small deviation can distort the entire geometry of the finished piece. One can notice how a hydraulic mechanism applies gentle upward pressure once the aluminum has solidified, freeing the solid metal from the steel walls with a slow, steady motion. Mechanical clamps then secure the heavy ingot, often weighing several dozen kilograms, lifting it out of the casting channel. The ladle and manipulator move with the hiss of hydraulics as the metal is placed onto a parallel steel conveyor. The sound of metal sliding and scraping reverberates through the foundry, while each ingot surface still emits a faint red glow from residual heat. One after another, the ingots are released in perfect synchronization with the machinery and arranged neatly along the moving belt. Sensors immediately scan each piece, verifying its shape and dimensions to confirm that no distortion occurred during the release from the mold. Everything only gets more complicated as rows of solid aluminum ingots continue their steady advance, aligned like uniform metal blocks. This signals the completion of a full production cycle. The material leaves the casting zone, transitioning into a calm stage as the heat gradually dissipates. 8 to 10 inches is the standard initial thickness for the solid aluminum ingots as they emerge from their molds. Why must these massive blocks undergo intense heating before they ever touch the rolling mill? It seems simple to apply pressure immediately, but in reality, the molecular structure of the cold metal would resist deformation and fracture under the rollers. The preheating furnace ensures the aluminum is softened and brought to an optimal thermal state for the mechanical transformation ahead. One can notice how the heated ingots are systematically transferred from the furnace to the rolling line with slow, deliberate movements of the conveyor. Immense pressure is applied as each prepared ingot passes through a series of counter-rotating steel rollers that compress and stretch the metallic block. This physical operation does not occur in a single pass, but is repeated across multiple specialized rolling stands positioned in a sequence. The gap between each pair of heavy rollers narrows gradually with every transition, forcing the metal to elongate. It is visible how an ingot measuring several inches thick is steadily reduced into a thin, uniform sheet of metal. But this is just the beginning. The equipment gradually deploys a fine water mist cooling system that stabilizes the aluminum surface throughout the entire high-pressure process. This precise moisture application prevents the formation of cracks or structural deformations that would otherwise be caused by the accumulation of excess heat. By the final stage of the reduction, the aluminum sheet reaches its precisely specified thickness, which in some cases measures only a few hundredths of an inch. The metal is guided forward as a continuous shimmering strip and is then tightly wound into large, heavy coils. These standardized semi-finished coils represent the culmination of the hot rolling phase and are now prepared for the next level of production. Further processing steps such as cold rolling, precision cutting, or industrial stamping await the material in the subsequent departments. The aluminum is now in a versatile form, ready to be integrated into various manufacturing chains. This concludes the primary shaping stage, moving the production flow toward its final technical requirements. 800 million aluminum cans enter global circulation every single day, becoming an inseparable element of the modern landscape. Why does such a ubiquitous object deserve meticulous attention after its contents are consumed? The answer lies in the unique molecular structure of the metal itself, which allows it to transition from a discarded container back into a high-grade industrial resource without any loss in quality. One can notice these silver cylinders appearing in vast quantities across supermarket aisles, stacked within cooling units at cafes, or distributed during social gatherings and quiet family dinners. But this is just the beginning of a cycle that depends entirely on a single physical movement. The equipment at sorting facilities is already calibrated to handle this influx. At first glance, an empty can is merely a piece of refuse, but in reality, it stands at a critical technological crossroads. If a consumer places the container into a specialized recycling bin, the potential for near-endless renewal is immediately unlocked through a series of automated industrial processes. In regions where deposit return systems are operational, more than 80% of all cans are successfully reclaimed from the public. It is visible how these containers are compressed into dense bales before being transported to smelting plants for high-temperature processing. The process is only gaining momentum. Within just a few weeks, the recycled material is transformed and returns to the shelf as a brand new product. Aluminum remains one of the most sustainable materials ever engineered by human technology. Yet its efficiency is tethered to human behavior. Cans that are incorrectly tossed into general household trash bypass the recovery sensors and end up as a permanent environmental burden in landfills. The contrast is stark, as the energy required to recycle aluminum is only 5% of what is needed to produce primary metal from ore. Everything only gets more complicated when the cycle is broken by improper disposal. One can notice how the material lays dormant in the earth instead of returning to the furnace. Therefore, the simple act of choosing the correct bin becomes the primary engine for the entire green industrial cycle. Each time a container is dropped into a recycling receptacle, it constitutes a technical contribution to a closed-loop system. This keeps the mechanical conveyors of the recycling industry moving and ensures that the metal continues its journey through the production chain. Transition to the next level occurs as the discarded item is reclassified as a raw material for the melting process. From here, the transformation moves to the next phase of processing without any unnecessary waste. Thus, the aluminum reaches the standard ready for its next life cycle through a series of calculated industrial steps. 100% of aluminum can be recycled infinitely without losing its physical properties. Why do we observe this metal returning to the production line in a never-ending loop? It only looks obvious that used material should be discarded, but in reality, every fragment of scrap represents a saved reservoir of energy. This circular process ensures that what once functioned as a discarded container is reborn through intense heat, transforming back into high-strength industrial components. The material follows a path of constant renewal that avoids the need for primary extraction. One can notice how the sorting equipment separates various alloys to maintain the purity of the metal stream. Beverage cans, structural window frames, and even complex aeronautical parts all share this singular origin point of recycled scrap. The process is only gaining momentum as more material enters the furnace.